In this video, we're going to learn how to analyze the graph of a rational function. This is part 2 of a two-part video lesson, so if you haven't watched part 1 yet, I would go watch that before you watch part 2. Now, to continue where we left off, we went over the series of steps you can take to analyze a function, so now I want to go into a more in-depth problem with graphing. So we'll start first by factoring the numerator and denominator of this rational function. So the numerator can factor out a 3x and be left with x minus 1. And the denominator can be factored into x plus 4 times x minus 3. The reason why we start by factoring is to find the domain of our function. Where is the function undefined? The function is undefined whenever a factor in the denominator is 0. So if x plus 4 was set equal to 0, negative 4 would cause that factor to become 0. And 3 would cause the right factor to become 0. So my domain will be all real numbers for x, such that x does not equal negative 4 for the x plus 4, and x does not equal 3 for the x minus 3. But everywhere else, it should be defined. Then you would put it in lowest terms. Here, none of the factors cancel out, so this is lowest terms. Now we'll find the intercepts of the graph, starting with the y-intercept, which is just plugging in 0 for x. So if you plug in 0 for x, you'll get 0 minus 0 over 0 plus 0 minus 12, so 0 over negative 12, which is 0. So my y-intercept is the point 0, 0. So it crosses through the origin, which so happens to also be an x-intercept when it goes to the origin. So I also have an x-intercept at 0, 0. My x-intercepts are any numbers of x that make the numerator equal to 0. So I already got that. If I plug in 0, I'll get 0 up there. But if I plug in 1, I'll also get 0. So my other x-intercept is 1, 0. Now, if you want to know how it behaves around those zeros, plug in 0 for x into every factor besides the factor that gives you that 0 in your numerator. So if I plugged in 0 into everywhere but the x by itself, I would get 3 times negative 1, which is negative 3, over 4 times negative 3, which would be negative 3 over negative 12. So the slope at this point should be a positive 1/4. So I should be increasing through that point at a shallow slope. And if I plugged in 1 everywhere besides x minus 1, I would get 3 times 1, which is 3, over 5 times negative 2. So 3 over negative 10, negative 3/10. So I know that I probably go up shallowly through that point and down shallow through the other points. So it kind of gives you an idea of how you interact with those intercepts. Now next up, we're going to determine the vertical asymptotes. These are everywhere the function is undefined still that didn't get canceled out. So my vertical asymptotes would be at x equals negative 4 and x equals 3. They typically match where your domain is undefined. And lastly, let's look for any horizontal or oblique asymptotes. The powers are matching, so I'm going to have a horizontal asymptote. So I'll use long division to see where that would be. So x squared plus x minus 12 goes into 3x squared minus 3x, how many times? Well, I would look into how many times does x squared go into 3x squared? 3 times. Now multiply that entire divisor by 3. So I'll get 3x squared plus 3x minus 36. Then subtract that. I'll get 0. Negative 3x minus 3x is negative 6x. And then 0 minus negative 36 is plus 36. So I get 3 with a remainder of negative 6x plus 36. So my horizontal asymptote would be y equals 3, whatever you get in that quotient. So I have a horizontal asymptote at y equals 3. Another way to get this horizontal asymptote without dividing is if the powers match. Just put the leading coefficients in front of both of those terms over each other. So 3 over 1, that's 3. That's the horizontal asymptote. If they don't match and it's bigger up top, then you have to go through long division for sure. Now next we just see if there are any points that lie on that horizontal asymptote. The way we find this is to just set our function equal to our horizontal asymptote. So I would set 3x squared minus 3x over x squared plus x minus 12 equal to 3 and solve that equation. So I'll multiply each side by x squared plus x minus 12. Give me 3x squared minus 3x equals 3x squared plus 3x minus 36. I can subtract 3x squared from both sides. Give me negative 3x equals 3x plus minus 36. I can subtract 3x from each side, so give me negative 6 equals negative 36. And then x equals 6. So at x equals 6, it touches my horizontal asymptote. So now let's draw these asymptotes onto our graph. So one's at negative 4. And one's at positive 3. And then I have another one that's horizontal at y equals 3. But at x equals 6, my function touches that asymptote. So I'm just going to put a point there. Because when x is equal to 6, the function's equal to 3. Now let's break down our function and see if it's located above or below the x-axis so we can see how it behaves with these asymptotes. The way we break up our interval is everywhere our numerator or denominator is equal to 0, we split up the interval that way. So the smallest number that we get is negative 4. The next size number we get would be 0. The next one we get would be 1 from x minus 1, and then 3 from x minus 3. And now we broke up our interval into 1, 2, 3, 4, 5 different intervals. One that goes from negative infinity to negative 4. One that goes from negative 4 to 0. One that goes from 0 to 1. One that goes from 1 to 3. And one that goes from 3 off into infinity. So 5 different sections of our graph. What you can kind of see down here is from negative infinity to the green asymptote, from the green asymptote to 0, from 0 to 1 between those two zeros, then from 1 to the green asymptote, and then from the green asymptote on. Those are the 5 spots. So what I'm going to do is pick up a number in each of these intervals. So in that first interval, I can pick negative 5, and usually you want to get as close to 0 as you can to keep them small. Here, I can't pick 0, but I can pick negative 1, negative 2, this is right in the middle, or negative 1. Between 0 and 1, I have 1/2. Between 1 and 3, I have 2. And then from 3 onward, I'll pick 4 to get as close to 0 as I can. Now, when I plug in these numbers, when I plug negative 5 into this expression, you can just use a calculator, but I'll speed up the process. When you plug in negative 5, you get 11.25. When you plug in negative 2, you get negative 1.8. When you plug in 1/2, you get 1/15. When you plug in 2, you get negative 1. And when you plug in 4, you get 4.5. Now, its location, since this is positive, that would be above the x-axis. This is negative, so it's below. That's positive, so it's above. Negative 1, so we're below. And positive means we're above the x-axis. So we're above it, we're below it, we're above it, we're below it, we're above it. So when I go to graph, I'm going to plot these points. When I plug in -5, I get 11.25. So -5, 11.25. I'm counting by twos here. So it's between 10 and 12. So 11.25 is about right in the middle. It's a little bit above the middle. When x is -2, y is -1.8. So -2, -1.8. Again, I'm counting by twos, so it'll be right above that line. When x is 1/2, y is 1/15. So it's really just above that line right there. I'll put a little bit more above that spot so you can see it goes above the x-axis. And then at 2, y is -1. So we have the point 2, but then -1, so right in the middle here. And then lastly, I have 4, comma 4.5. So 4 and 4.5, if this be 4.5, it'll be about right there, because it'll be 6 on the purple line. So now when I go to graph, I'm checking out its behavior, how to figure out each asymptote. This one's above the x-axis. So since I know it doesn't cross the purple line anywhere else, I know it's going to go down and flatten out along the horizontal asymptote, then go up the green asymptote. Then down here, I know that between -4 and 0, it's below the x-axis. So I'll follow up from the bottom of this asymptote, go through the point towards the first 0. Between 0 and 1, it's above, so I have this slight moment where it's above the x-axis. And then after, from 1 to 3, it's below, so I'm going to go through this next point and then just continue downwards along my vertical asymptote. But now, for this next part, ooh, I drew my horizontal asymptote in the wrong spot. I don't know if you noticed that. That, according to my graph, is on the line y equals 6. So I'm going to erase that and redraw it in the correct spot. That point's in the right spot, but the other point wasn't. So I have to actually put it at y equals 3, which would actually be between 2 and 4. So I'm glad I caught that before it was too late. That's where the horizontal asymptote would be, at y equals 3. And then that point where it crossed at x equals 6, be right there. So now, this line up here would actually curve and go down much more. Be closer to that y, the horizontal asymptote. Curve down it. And up here, I know that between 3 and onwards, always above the x-axis. So I come from the top of this asymptote. It goes through this point, and then I know that it crosses through this point. And I think it's just going to be right below it. But if you want to be extra safe to see if it's now below the purple line for the rest of the function, all you have to do is just plug in a number after 6. So for example, 7. If I plug 7 into this function, I'll get the value 63/22, which is just below 3. So I can see that it goes below that line, then flattens out. So here's what that graph would look like. So that's a more in-depth example that has lots of turns and different things that can happen. Now I'm going to go over one final thing that can happen while you're graphing with this problem, which we're going to go through it and still factor and graph and do all the same analysis as we normally would. But we're going to start with factoring the numerator, which factors into 2x minus 1 times x plus 2. Oh, 2x minus 2. Sorry. Over difference of squares, x plus 2 times x minus 2. So my domain is going to exclude negative 2 and 2, since that would make my function undefined. Negative 2 because of x plus 2, positive 2 because of x minus 2. So my domain will be all real numbers x, such that x does not equal negative 2 or positive 2. Now I'll put this into lowest terms. I actually have a factor that can cancel, so I'm going to get rid of that factor, and I'll be left with 2x minus 1 over x plus 2. So when I go to look for my intercepts, I'm going to use my lowest terms function. So my y-intercept is going to be at negative 1/2. If you were to plug in 0 for x, you would get negative 1/2 for y. So I'll put my y-intercept at 0, negative 1/2, which I'm counting by 2's again, so it's going to be up there somewhere. And then my x-intercept would be anything that makes my numerator 0. So if I set 2x minus 1 equal to 0, I would get x is equal to 1/2. So 1/2, 0 is my x-intercept. So 1/2 here, 0. Now the slope at that spot, if I plug in 1/2 into everywhere but that spot, you can learn what its slope would be. So here, if I plugged in 1/2 at the bottom, I would get 1/2 plus 2, which is 5/2, which flips to be 2/5 times that 2, which would be 4/5. So it goes up at a positive slope, which you can kind of see if it goes from that y-intercept through that point, it should be a positive slope. And then next up, we're going to find all the vertical asymptotes, again, using the lowest form. So again, we got rid of x minus 2, so x equals 2 wouldn't be a vertical asymptote. Just x equals negative 2. And then we'll use that little trick I showed from earlier to find the horizontal asymptote because the powers match. I'll just put the coefficients over each other. So 2 over 1, which is 2. So I'll have a horizontal asymptote at y equals 2. And if I used long division, I would find that as well. So let me draw that in. So that'll be right here on the first tick mark since I'm counting by 2's. And now I will split up my interval using the zeros from the numerator and the denominator, which there are only a few here. Now, I would definitely have to use negative 2. And then positive 1/2. But the question is, should I use x equals 2 since I would have made my numerator 0 earlier? Well, it can't hurt to check. So I'm going to use 2 as well. Even though I canceled it out, I'm still going to include it here to make sure that I don't miss any changes that might happen. So now my interval goes from negative infinity to negative 2, negative 2 to 1/2, 1/2 to 2, and then 2 to infinity. So between negative infinity and negative 2, I could pick the number negative 3. Between negative 2 and 1/2, I can pick the number negative 1. Between 1/2 and 2, I could pick 1. And from 2 onward to infinity, I can pick 3. So plugging in negative 3 into my original function, I can get positive 7. When I plug in negative 1 into this function, I get negative 3. When I plug in 1, I get positive 1/3. And when I plug in 3, I'll get a positive 1. So all this tells me is that since this is a positive value, it's above the x-axis. This negative value means it's below the x-axis. Positive means it's above. And then even after this 2 that was canceled out, I still remain above the x-axis, which I kind of expected since I'm really using this function for most of it. So I want to plot the points. Negative 3, 7. Negative 1, negative 3. 1, positive 1/3, and then 3, 1. So negative 3, negative 7, negative 1, negative 3, 1, 1/3, so just above the x-axis, and then 3, 1, 2, 3, 1, right in the middle. So when I go to graph this, I can tell when I'm analyzing behavior of these asymptotes, when I go to graph it, is since I know this is always above the x-axis, and I also forgot to check to see if this function could cross that asymptote, so I'll check that really quick. Because I don't know if there's any points that are on this line yet. So if I set 2x minus 1 over x plus 2 equal to 2, and try to solve, I'll get 2x minus 1 is equal to multiply each side by x plus 2, so 2x plus 4. Subtract 2x from each side, and you'll see here negative 1 cannot equal 4, so it never crosses that purple line. So knowing that, it's going to go up the green asymptote curve, but never cross the purple asymptote as it goes down. And over here, from negative 2 to that 1/2, where it crosses the x-axis, it's below. So it's going to go from following this green asymptote up and then curve through your points. And then from negative 1/2, from 1/2 onward, it should be above the whole time. But what happens at 2? It's undefined at 2, so I know I can't put a point there. So at the value of 2, wherever that would be, the best way to find that is just to plug 2 into the simplified version without the x minus 2, which would be 2 times 2 is just 4 minus 1, 3 over 4, so 3/4. At that exact spot, at 3/4, I'll actually have a hole in my graph because I know it's undefined, but there's no asymptote that would go there. So I just put a hole in my graph at that spot. And that is how you analyze the graph of a rational function.